So let's take a look at the Gulf Stream. The Gulf Stream is known as a western boundary current. And it's a western boundary current. It's called a western boundary current in relation to where it sits in the Atlantic Ocean. It sits on the western edge of the Atlantic Ocean. So even though we might think we're on the east side of North America, in terms of the Atlantic Ocean, the Gulf Stream is on the western end. The Gulf Stream is a result of that northward flow of water from the tropics, the subtropics, and because of this, we see some very significant differences between the western boundary currents and the eastern boundary currents. The Gulf Stream here, once again, this image is colored according to temperature, is this area shown in red where we see some of the warmest temperatures of water in that region. Benjamin Franklin of the Flying a Kite with a Key at the End and the Lightning Storm fame published about the Gulf Stream way back in 1769, and he actually published the first ever chart. Remember, this is a map of a current. What he got his data from was he had a cousin, Timothy Folger, who was a merchant in Nantucket, and other merchants who would rely on shipping goods to and from Europe, and they always took advantage of moving along this current because that allowed them to travel much faster. Quite often mail was being moved, transatlantic mail was being moved between England and the colonies at the time, and by using this current, taking advantage of this current, they were able to very quickly move mail from North America over to Europe. So based on this data collected from Timothy Folger and other sailors at the time, Benjamin Franklin produced a chart of the Gulf Stream as it was known in 1769. Why do we mention Benjamin Franklin? Well, in 1969, there was a mission called the Gulf Stream Drift Mission, where people traveled in a submersible and traveled the length of the Gulf Stream. The submersible they traveled in was named the Benjamin Franklin because he was the one who sort of first identified the Gulf Stream. The idea of the mission, and this is where sort of things are all interconnected in oceanography, was conceived by Jacques Piccard, the same guy who went down to the bottom of the Challenger Deep. Basically what happened is the submersible entered the Gulf Stream off of West Palm Beach, Florida on July 14th of 1969, and then just basically drifted in this current, drifted in the Gulf Stream until it finally ended up off the coast of Halifax around August 4th of 1969. You had 30 days, 6 men in one sub, a small enclosed place. NASA once again was also interested in this because it showed you what happened when you took a number of people and placed them in a small confined place for a number of days. Same thing you'd happen to do on a moon mission. What did they discover on this mission? Well, they discovered that the Gulf Stream is fast moving and it travels at a speed on average about 6.4 kilometers an hour to a depth at 450 meters. At the surface, it's a little bit quicker, 9 kilometers an hour, and the difference in speed or velocity being explained by the fact that there's a lot less friction at the surface. As you go deeper and deeper into the water, friction and the progressive accumulation or concentration of friction progressively slows the movement of water down. Water can travel greater than 160 kilometers a day, so you can have the movement of water over great distances within the Gulf Stream and any other sort of western boundary current. Here's another image, once again colored. This one's based on speeds, and you can see sort of the quickest speeds do occur within the Gulf Stream. The Gulf Stream, as well as any other western boundary currents, are responsible for the transportation of warm water either northwards or southwards. This has some important facts. This is one of the reasons why Bermuda looks like this picture. Bermuda sits off the coast of North Carolina, someplace that's considerably cooler than Bermuda, but yet you can still go visiting Bermuda throughout the year and swim in warm tropical waters. The Gulf Stream, too, this movement of warm water towards the pole and then cutting east across the northern part of the Atlantic, helps to keep parts of Europe warm as well. This is why London typically is much more warmer as a capital than a lot of places in Canada, even though we might sit on the same line of latitude. From initial studies in 1969, as scientists traveled aboard the submersible Benjamin Franklin up to the present day, we keep developing a better and better picture of what the Gulf Stream is like, and with it we start to get an idea of what all western boundary currents have. And we see that they have some pretty typical features. We find that they're narrow, so they might have a width of 100 to 200 kilometers wide. They're not a very thick or very wide current. We find that they move fast. We also find that the waters that form this current are fairly deep, and that it moves warm water poleward. This is typical of all western boundary currents. The other thing we see is that the water itself is often nutrient poor. And another thing you might note in this image right here is that the air above the ocean also sort of shows where the Gulf Stream is. The air is typically clearer, there's less clouds above the warmer Gulf Stream. 5 subtropical gyres means that we have 5 western boundary currents. And these currents include the Gulf Stream, the Kuroshio current or the Japanese current, the Brazil current, the Agulhas current, as well as the East Australia EAC current of the South Pacific. Another common feature of western boundary currents are eddies. Eddies are basically a whirlpool, and what we see is a circular motion of water. Where eddies form is often along the edges, the boundary between a boundary current and the water surrounding it. What happens is there might be some disruptions along this boundary, and this has caused meanders to form. The meanders might connect to eddies that are already pre-existing within the water itself and basically trap cold or warm water in the centers. Cold water eddies form in the Gulf Stream for this example. Warm water eddies will form to the north of the Gulf Stream. Basically what happens is the warmer water will kind of loop out of this disruption, encircle that eddy. We get clockwise movement of warm water and counterclockwise movement of cold water. We also know that these eddies are present. When we did have that expedition aboard the Benjamin Franklin submersible, they got caught in an eddy for a couple of days and basically went around and around and didn't make any significant distance gains within these days. Eventually they broke free of the eddy and were able to drift further north to Halifax. These eddies can become completely isolated, so what you have is this little pocket of cold water and warm water, the warm water of the boundary current, western boundary current, or you're going to have a pocket of warmer water sitting in cooler water just offshore. And here's a lovely satellite image of one of these eddies in the Kuroshio current off of the eastern coast of Japan. We also have eastern boundary currents, and eastern boundary currents could be thought of as the counterpart to the western boundary current. So in the North Atlantic gyre, we have the Gulf Stream as the western boundary current. Over on the eastern side of the Atlantic, we have the Canary Current as the eastern boundary current. We find some significant differences between the currents. We find that these boundary currents are shallow and broad. They might be, instead of 100 to 200 kilometers across, extend up to 1,000 kilometers across. Instead of moving warm water towards the poles, it moves colder water towards the equator. The boundaries between the currents aren't as defined as we might have seen in the examples of the Gulf Stream that we looked at. And we see that there's very little formation of eddies, and not a lot of water is transported within these currents. They don't move as quickly as the western boundary currents do, and because they're shallow, they don't move quite as much water as well. Another thing to note here, a little bit more significant than the absence of clouds over the Gulf Stream, is a complete absence of clouds over the Canary Currents. And this has to do with the fact that we have really cold water or colder water moving through at this point. We also find that nutrient levels are greater within eastern boundary currents. So here's a picture of the Benguela Current that sits in the southern part of the Atlantic Ocean off the coast of Africa. And this image has been processed. It shows levels of chlorophyll in green. Chlorophyll is indicative of how much photosynthesis is going on within the oceans. Photosynthesis produces nutrients, energy and nutrients that are needed by anything else in the food chain within the oceans. So we see that this water, even though it's colder, it's much more productive. It's much more nutrient rich than waters of the western boundary current. Just as we did with the western boundary currents, we have 5 eastern boundary currents as well. This map only shows 4 of the 5. The Western Australian Current, which operates in the Indian Ocean, just sits off the coast of Western Australia, and it's covered up by the border in this image. So we have the Canary Current, the California Current, they're in the northern part of the hemisphere, the Benguela Current, and the Peru Current in the South Atlantic and South Pacific, respectively. So the eastern boundary currents are currents that are moving colder water towards the equator. The result of this is that we quite often see deserts, especially along the coastline of Africa, that extend all the way up to the ocean itself. And this is because of the presence of the Benguela Current just offshore. The Benguela Current, once again, cold water, which means that the air above it is cooler. What we see is it's a dry air that's not much moisture in it. This moisture then cannot move over in top, or moisture cannot move over in the form of clouds over top of the land, where it will eventually rain. So we see that deserts, especially along coastlines, are often associated with areas that are along eastern boundary currents as well. Why do we see these differences between eastern and western boundaries? Especially, why are the differences in the fact that one is narrow and one is deep and one is very shallow and broad? And this is due to something that we call westward intensification. What we see has a combination of the ocean surface winds, it's a combination of gravity and Coriolis effect. All of these three things work together. It causes a buildup of the western boundary ocean current. What does this mean? Well, what we see is if we look at this diagram here, and we're looking at both sort of from side view as well as from the top, we see that there are essentially holes in, or not holes, sorry, but there's hills in the ocean. Water tends to pile up in the direction that the wind is blowing. So as the wind is blowing across the water, it's not only moving the water, but it's piling the water up in that direction as well. Water pressure is higher in the piled up area, and what happens is that gravity will want to pull water down the slope. So we have gravity trying to pull water down the slope. But due to the forces of gravity, the Coriolis effect, even the energy that is emitted by the sun, we find that water will move in a circular pattern called a gyre. Now, what happens is the Coriolis effect makes the water move to the right in the northern hemisphere and move to the left in the southern hemisphere. This hill of water, though, isn't located in the middle of the ocean. Remember that not only is the Earth rotating, not only do we have water piling up because wind is pushing it, but the rotation of the Earth as well pushes the water to the west side of the ocean basins. What happens then is water in the west side of the ocean has to squeeze between this hill of water that's sort of created by the blowing of the wind, and the continent. In this case here, if we're talking about the Gulf Stream, North America on the left-hand side of the Gulf Stream. So all of a sudden now you're trying to push water through a very narrow space. What does this do? Well, it makes the water go faster and that water to be deeper. Water on the east side of the hill has a much wider path and slows down. So this would be water that belongs to the eastern boundary currents. This is what we call a western intensification. So we create this hill in the ocean. It's not a hill that you're going to sail along and see, oh, geez, there's a hill. It's a hill with a very low slope over a large distance, created by wind pushing the water up into a bulge. The rotation of the Earth is trying to move the water towards the left. You throw in the Coriolis effect, and what happens is we get this intensification of flow on the westward side. And on the eastward side, where we find, for example, the Canary Current, things are a little bit more relaxed, a little less intense. One final thing I want to say that might make this a little bit more clear, you can think of as the western boundary currents are narrow and fast because they have less width to travel through. So it's sort of like if you have a water hose, you're trying to water your garden, you want the water to go a little bit faster, have a little bit stronger of a flow. You basically squeeze that garden hose together. That's going to increase the flow rate of your hose and get a much narrower and faster flow of water. This slide does a really nice job of summarizing the differences between western boundary currents and eastern boundary currents. Once again, if I was studying for an exam, I'd look at this and say this makes an excellent sort of multiple choice question or true or false question. Something like professor could ask, which one of these is a characteristic of western boundary currents, and you have to pick the right one. So definitely take a look at this, definitely review what the differences are between the western boundary currents, the eastern boundary currents, and know that the differences between these currents is due to westward intensification, the fact that we have this hill in the middle of the ocean. The final currents that make up a gyre are the transverse currents, and these are currents that either flow east to west, known as equatorial currents, or currents that flow west to east, known as northern or southern boundary currents. There's nothing really significant to say about these currents. They're driven by the trade winds and the westerlies and basically move water that's carried by either the western or eastern boundary current over to its counterpart. We observe that some marine organisms take advantage of this system of currents. For example, here is a sea turtle, a Florida head loggerhead turtle. They leave the beaches that they're born on, migrate east to the Gulf Stream current, and then basically sit there and ride the North Atlantic Gyre around for a number of years, especially as it flows around the Sargasso Sea. So these circulation patterns in the ocean can sometimes provide valuable routes by which marine organisms such as the sea turtles travel. And in fact, if the migration patterns of Florida loggerhead turtles are tracked, we find that it basically mimics the North Atlantic Gyre and the movement of the North Atlantic Gyre. We find that they spend many warm years sort of in the warmer southern waters of this gyre, a place called the Sargasso Sea. They might not follow the exact same path, but eventually all of them will head east and then move south before returning home to lay their eggs. There is a sixth major circulation pattern that we haven't talked about yet. So before we looked at five subtropical gyres, also known as geostrophic gyres. They have what we call geostrophic currents. A geostrophic current is an ocean current in which the pressure of the differences in water pressure is balanced by the Coriolis effect. But what we see here is that we have these five gyres and their associated currents within them, and then there's a sixth one. And the sixth one is known as the Antarctic Circumpolar Current, or west wind drift. It's this endlessly flowing eastward Antarctic Circumpolar Current driven by westerlies, which is a type of wind, and it just continually travels in one direction around the Antarctic.